All right. So today we are going to, okay, Hanwen, so you are now joining.
Hello, Professor.
Yep, so thank you. So we are about to start. We have been waiting for you. So, all right. So we can now start. Oh, okay. So let me, wait till I ask, do you have any questions first?
No question? Okay.
Okay, very good. All right. So if not, then we will just start chapter 11. So chapter 11 is about the Lebesgue theory. So in we actually know the define what is a Riemann integral. So when you are given a function and we want to define the Riemann integral, say from a to b of this function fx, the way we do it is that we just decompose these into small pieces, and then we use the rectangles, the area of the rectangles to approximate the area under the curve, and then this would be defined as the limit as this delta of this partition, which is let's call it delta. The partition is the maximum of the intervals of maximum length of subintervals. Of subintervals. So as this maximum length of subintervals goes to 0, to look at the Riemann sum, which is xi star delta xi. Delta xi is the length of each subinterval. Xi star is just any points, and this is the Riemann sum. And this limit, if it exists in terms of epsilon, you can rephrase it in terms of epsilon data language. Then you would have you would get the precise definition. Now, Riemann, this theory of Riemann has obviously is a very useful concept, but it has its drawback theoretically. One of the things is that we know that this function, if a boundary function is Riemann integrable, if and only if it has its set of discontinuity has a zero measure. So we define a zero measure already. We can actually we will come back to this point again. So this kind of function is too restricted, but like for example, we have been using this as our example. If horn x is irrational, or an x is rational, 0, then the Riemann integral does not exist. So this is we are a little bit too restricted. The concept of Riemann integral is a little bit too restricted. Another thing that we know is that when we define the Riemann integral, when we're trying to interchange the limit sign and the integral sign, Paul, what are the conditions that we usually ask Fn to satisfy, Paul?
Uniformly continuous.
Uniformly convergent, right?
Oh.
Yeah. So you, in order to interchange these, usually require the conversion is uniform. Uniform conversion, as we see, is a very restrictive, very rigid, very restrictive condition. So this is another drawback for the Riemann integral. And Lebesgue discover or establish a theory which would generalize Riemann integral. One of the way to look at the Lebesgue integral, of course, we are going to learn about it more. Is that this when we partition these into subintervals, these actually are too restrictive. Now the way Lebesgue said is that, okay, instead of partition the domain, we actually partition the range. Now, when you partition the range, this piece, let's say this piece partition here, now then it would corresponding to a region here, but this region here actually may be more complicated. I mean, in this picture actually is also an interval, but in general, this here it could be more complicated. So the another way to look at the we are going to talk about Lebesgue integral is that instead of partition this interval from A to B into subinterval, we can partition into a more general set, which requires a Lebesgue integrable, measurable sets. We can partition in more general sets. And then this theory, the definition will still holds, but here we don't have the restriction that this partition of this AB is into subintervals. It could be like a partition in some of the rational numbers, some irrational numbers, or etc. It doesn't have to be an integral interval. So that is the essence behind the Lebesgue theory. So we are going to cover this chapter. We actually have two only today's lecture and on Monday's lecture. But let me ask you, on Wednesday, I'm going to kind of like have a next Wednesday, a week from today, I'm going to have a kind of like a problem sections that we can discuss problem more. If I have something left, I would want to cover on that on Wednesday. Would all of you available on a week from today at the same time?
Yeah, I'm available at that time.
Yes.
Paul?
Okay.
Yes.
Hanwen is also okay. Okay, so then we will have a kind of problem section or review section. All right, so we are now start with the theory. I would actually combine several sections together. Then the first section is going to be 11.1 to 11.4 together. So I would call it as Lebesgue measure. So we first define Lebesgue measure first, and then we will define Lebesgue integral. So now, what is a measure? What is a measure? So I would actually, these are the material in section 11.3, I slightly changed the order. So a measure space is just X, is just a set, a non-empty set, any set. And then we have a group of subsets. This M is script M is a collection of subsets. Of X. Now this, and then we have a function mu is defined on M on any subset in M is non-negative. This means non-negative. This is non-negative set function. So if you give a set, then you give your measure. Give a set in now this is this would we call the measure. Now this set we will call it as measurable sets. So we only define a measure on measurable sets, on the sets in M. Now, of course, these would satisfy several axioms. So M is a sigma ring. What is a sigma ring? A sigma ring is okay. So M is a ring. A ring, remember, M is just a set of subsets. So then it's called a ring here, means that for any subset A and B in M, in this M measurable set, A union B and A set minus B is also in M. So M is a collection of sets. This collection of sets satisfies the is closed under union, closed and set minus, closed under set. So i.e. M is closed under union and set minus. So you remember what is the concept of set minus, right? Set minus, like if this is A, this is B, and A minus B is this part. It's the things that are in A, not but not in B. Okay, that's set minus. And now sigma ring, sigma here just means countable. Okay, another way to say countable. Now a sigma ring means that here you only for a ring you only have union of two sets is also in two measurable set is also measurable set, but the countable sigma ring means that even if you have you have countably many subsets, those are from M, then the union, the countable union of them is still in M. So M is closed under countable union. Okay. Now, okay, so this now what is mu? Mu is the measure. So mu also is a non-negative. What we call as mu is a non-negative. Non-negative countable additive state function. What does this mean? This means that if you have A1, An that's countable remaining set in from M. Now, we also assume that Aj intersect Ak is empty. So this means that when J is not K, all right, that means that these are pair wise disjoint. So in that case, we would have that the measure of the union or maybe I just use N. The measure of the union is the sum, is additive, means that you do is sum of each individual measure. Okay. Now, so first of all, countable additive implies finite additive. So if you have A1, let's say you have A2, and then you like to find mu, first of all, now, okay, let me mention something here. This actually, in this case, I have these are non-negative numbers, but it could also be infinity. The measure of a set could also be positive infinity. So so if you have, first of all, okay, let's see this. So let me make some remark here. Now we will come back to this point. First of all, empty set is always in M. Why is that? Because we have a set A, right? This M, the measurable set, is a non-empty correction. So if it's empty, then you have nothing to talk about. So we just assume that what's wrong with my iPad? So slow. M is a non-empty correction. Now, A set minus A, because it's closed under set minus. A set minus A would be what? Empty set. This means empty set. So it must be in M. So the empty set is always a measurable set. Thirdly, what is the measure of an empty set? So an empty set, you can also write it as a union, infinite union of empty sets. It's still empty, and then this would be infinite sum of this. So this would force, I guess you do in here, we would assume that at least one of these is non-zero, is finite. So then this, you have a set equals is finite. So from here we know that mu phi must be empty set must be 0. Now then we come back to this where countable would countable additive would implies finite additive, because if you're finite union, you can just write it as A1, A2, and then empty set. So therefore, it would be mu A1 plus mu A2 plus mu empty set, which is 0. So therefore, we have this equals to this. Now, so for these two, for this additive property to be true, we must assume that this set A and A1 and A2 are disjoint. What happens if you have two sets? Let me just write it as A and B. If they are not disjoint, then what do you have as the measure of A union B?
Zero measure.
So this would equal to what? The measure of A plus the measure of B is that all? Now this the intersection is non-trivial. Right?
Minus the measure of A complement B.
A intersection B, right? So this is A intersection B, correct? So because the measure of this, when we do it in A and when we do it B, it counts twice. So we need to minus it out. So this is exactly as what you learn in the countings. So a measure, actually, this is a generalization, or another way to look at it's some concept from probability theory. A set here, a measurable set, in the terminology of probability, is just an event. Now, if the measure, if this would be a probability that if you assume that the measure of the whole space is 1, this is probability theory. So if you learn higher, you will want to get into graduate class of probability theory, then you need to learn the measure theory. It's essentially another way to do measure theory. So that is very applicable subject. Now, okay, let's see how would one prove this. So all we have is that this function mu is additive. Actually, is countably additive. So I can write A union B as A minus B. So this part is A minus B, and this part is B minus A. Okay, so union B minus A and union A intersection B. Now, by the additive property, then we have this, the mu A minus B plus mu B minus A. These are now disjoint, all of these. Actually, let me rewrite. A. Now, this actually, we replace this by A intersection B. Instead of having B, and this also replaced by intersection B. So now this is A intersection B. This is also A intersection B. Now, then this is again by the additive property. This is A minus the union, the measure of the intersection, and this term here is mu B, the measure of the intersection, and then plus U A intersection B. So this and one of these cancelled, and you have one left. So these all these properties comes from the additive property. We didn't even use the countable additive properties. So we are going to define an integral on a measurable set, but that actually is not. This is a course called measure theory that deal with this abstract measurable thing. But let me go into the next section, which is about we now know measurable set. Then we need to now know what is the definition of measurable function. So the definition actually is quite simple. So suppose you have a f is a function from. So okay, let me be more precise. So x m mu is a measure space. Is a measure space. So this means that it is a set. This is a sigma ring. This is a sigma additive set function. All right. Now we say that a function f. Now this function here in the measure theory, we assume that this function take all real number, but it could also take either positive or negative number. So this we call this as extended real numbers. So now this function is called measurable function if the definition, if the set for any real number a the set of x in capital X, where fx is greater than a, is measurable. So is in M, in this good M. So okay, if now where do we have this? That is coming back from the way we are going to define the indigo, the Lebesgue indigo by partition on the range, not on the so that means that this, suppose this is my A, and these would be all the sets in this all the x, so that fx is greater than a. So these are the parts greater than a. These are parts greater than a. So let's say this is a, b. This is alpha, beta 1, alpha 2, beta 2. So this, in this picture, this is just alpha 1, beta 1, and union alpha 2, beta 2. Now, actually, you learn about these kind of sets before. Where in what context do you learn about this set? Ryan, do you remember?
No, I don't.
Okay. Paul or Hanwen?
Sorry.
Okay. Now we you learn this when you're trying to define continuity using this notion. So this function f is continuous if for any a this set is open. So in this case, these sets are open, but because my function here is continuous. So all of these sets must be measurable. So in this picture, in order for f to be measurable, the union of two open intervals must be measurable. So that is the concept of measurable. Now I would just state some property, and then now the theory now is actually quite is very abstract for you now. But I would just state some properties, and then we would come back to define the these next time. Now, so this property is that property 1 is F is all of these measurable. So okay, let me erase this function from X to R, and then the following are equivalent. First of all, we in our definition we said that this X in capital X, so that Fx is greater than A in M is measurable, and you can actually change this to greater than or equals to A, and or you can change it to Fx less than A for any A, okay? All of these are for any A. Any real number A, and then all right. Why is that? Let's see why is this implies this. If this is true, then this must be true. I will just give you a proof of one of these implications, or the others are actually similar. So remember our assumption on M, on script M, is that it's a sigma ring. So a sigma ring is a collection of sets so that it is closed under countable union and also under set minus. Okay, but I would write X I would actually okay, yeah. Let me, instead of putting 1 to back to 2, is actually, let me put 2 implies 1 that illustrate the idea better. Now I said, let's say if I assume that this property 2 is true, so then I write this as this. Greater than A so you said this A, if it's greater than A, so these are the sets here, then I can think of this as union of the sets of A minus 1 over N, where N runs from 1 to infinity. So I can write this as a union of X in capital X, Fx is greater than or equals to A minus 1 over N, where N runs from 1 to infinity. So now, if we know 2 is true, that means that this is in M. Now then M is sigma ring, that means that the countable union of M is also in M. So M is a sigma ring, implies that this set is in M, because it's a countable union of the sets in M. All the other direction can be proved similarly. Now so the so this is one of the property. I would also write down other properties that F is measurable. So are the absolute value of F, and then the limit of F, the sup of F. If you have a sequence, and then we call this F plus. F plus is just the maximum of F and 0. So that means that this is a positive part of F. In this picture, these are the things that are above the x-axis, and F minus, which is the minimum of F0, is the negative part, but you flip it over to the positive exit. Okay, so, and property 3 is if Fm is a sequence of measurable functions, then Gm, if G is if G is Gx is the sup of Fnx, or if Gx is the Hx is the lim sup of Fn as n goes to infinity, then Gx, G and H are measurable. In particular, limit of convergent. Okay, let me rewrite. In particular, if Fn if Fn converges to Fx pointwise, then F is also the pointwise limit of measurable functions is also measurable. Okay, so I would actually not going to put this for you. You can go back to look at these materials. Actually are in section 11.4. Now we have an abstract concept of measure, but that is not what we understand as the concept of measure that we learn in calculus. So how do we reconcile this abstract concept with the concept that we learn? So how do we define a measure in Euclidean space? Say on R1, how do we define measure? Suppose I have two sets, A and B. Then what would be how we would define the measure of this interval, say A to B? In this case, the concept of measure is what? Hanwen.
Sorry.
What would be a natural way if I want you to measure this interval? What would be the natural way to measure this?
The length.
The
B max.
length, correct? That is the length of this interval. And this actually, it doesn't matter whether you have a closed interval or you have an open interval. The length is going to be minus A. Now on R2, what would be the natural concept for the measure of a set? So in this case, the most natural is, say you have A1, B1 here, and A2, B2. So this is a rectangle. The measure of the rectangle, A1, B1, A2, B2 is what? Is the area, right? So is B1 minus A1 times B2 minus A2, correct? So that's how we define the, now in general, on RK, or let's call Rn. So this is the n-dimensional Euclidean space. Now we will say that a shell, an n shell, is just, or sometimes we just call it as an interval. This is not a right way, but it's, and the textbook is called interval, is just the set A1, B1, cross product AN, VN. Now this could be open set, open interval, or it could be half closed, half open. It doesn't matter. We all call them as an interval. And actually, it could happen that A1 equals to B1. In this case, this is reduced to a point, or it could, in the case of open, if A1 equals to B1, that actually is an empty set. So, but this could be reduced to a point. So, for this kind of interval, let's call this I. What would be a natural way to define the measure of this interval? Same idea, right? B1 minus A1 Bn times Bn minus An. So this is just the volume. This is the volume. And this in lower dimensional, this of course is the area. And this is the length. Now, so the problem with this is that if we just look at if we just look at the intervals, if we look at the concept of intervals, this concept of interval, let's say we assume that M is a correction of all intervals. Now, then, in order for the theory to work, we need to M need to be a sigma ring. So it needs to be closed under countable union, and it needs to be closed under set minus. But if you have two intervals, their union is not necessarily an interval, right? So therefore, if you have infinitely many interval, countably many interval, then their union obviously may not be an interval. So this definition is too restricted. It would not make it would not make this into a sigma ring because it's not closed. So this would not happen. Now, then we need to extend this to define M. What Lebesgue did was that, okay, you start with this concept of length, area, or volumes for the intervals in the Euclidean space, but then you throw a lot of more things into M, and then it would become a sigma algebra, a sigma ring, and then you modify your definition for mu, and then it would satisfy the countable additive property. So now we now learn how to construct of M mu. These are Lebesgue measurable sets. So the way you construct this Lebesgue measure set is you start with interval. So these are I case this. Now then you enlarge it to have a finite or finite union of intervals. Or union of finite union of intervals, and this set we will call it as epsilon. This would call as the we will call this any finite union of intervals we will call as elementary sets. Now, but this still is not sigma. I mean, E is still not is still not a sigma ring because it's finite. So when you have countable, then it's not. So we need to enlarge. I mean, on E, well, we can generalize mu. So we can generalize mu to define on E So that is just defining that if you have I1, this IK, and then these are pairwise disjoint, and then this is just the sum of this. So therefore, E is now a ring, and this is now finite additive. So but it's not countable yet, and E is not closed under countable union. So but however, we make an improvement. We made the first step in our construction. Now, in order to generalize these, we now define from mu. Mu is now defined on elementary on all elementary sets, and mu is now additive, finite additive. So, but then we define what we call as define an outer measure. We will call it as mu star. Mu star is on a set E is defined as the infimum of the unit of the sum of the measure of AN. Sun is countable sun for now. So this infimum is you have E, you can cover E by a countable union of measurable sets. All the ANs are measurable. No, but actually are elementary. So okay, let me just say that E is not is a set like this. Now we define the we cut this into small pieces. And then we just cover these by all these rectangles, these disjoint rectangles that at least it touch this, then we will use it. This we will need to use. Oh, okay, that's good enough. Now, then we sum all these area of these rectangles. So this we know how to define. And then we sum the area of these rectangles, and then we take the infimum of all possible covering by measurable by elementary sets. So as you keep divide this thinner and thinner, you know that this is going to become closer and closer to the measure of E. Actually, we do not know that E we can define a measure yet. We can only define a counter measure. Now, the way we define this outer measure, then it would, however, this outer measure would satisfy two property. So the outer measure of any set E is equals to the measure of E, that as we define it, if E is an elementary set, is in discrete E, is a finite union of intervals. And secondly, however, the bad thing about this E is that E would, we would only have what we call as the subadditive property. So even if these are disjoint, if you have a countable union, this would not equals, but less or equals to. So this for any set En in, oh, I use N here. So let me use, my dimension is N, so I need to use J here. I need to use J. I need to use J and any E J in our subset of R N. So it is not an equality, it is only an inequality. So that means that this still not a measure. The reason it's not a measure is because it is it does not have the sigma additive property. It only have this what we call as sigma sub additive property. Now, so the point is that now we can define what is from using the outer measure. We can define what do we mean by M. We can define M. Now, what is M? In order to define M, we said that a set A, let's just say set A is Lebesgue measurable, is we call it a mu measurable. Or if mu is defined in this way, mu is defined in this way, then it is Lebesgue measurable. If there is this, if A is a union of A, J, where is a countable union of AJ where each AJ is what we call as finite mu measurable. So what it means is that I would each aj is a limit of some set, I will call it a j k as k goes to infinity. Each of these are elementary sets. So a set is finite U measurable, means that this set can be approximate by elementary sets. Now, what do we mean by this? A set approximate this set. What it means is that the outer measure of ajk minus aj and aj minus ajk is goes to 0 as k goes to infinity. So that is the concept of what it means. Okay, so let me just draw a picture. So let's not thinking about aj. Let's think of this as set b. We said that bk opposes a. What does it mean? Means that you look at their. This is what we call symmetric difference. So you look at the difference of these two sets. These are the difference of the two sets. So this union, this symmetric difference, the outer measure of the symmetric difference, which are the red thing, bz minus bk, would go to 0 as k goes to infinity. So now then we now know the set M. M is just the limit of is the union, countable union of a finitely mu measurable sets, which is the limit of elementary sets. Now, it turns out that once you construct these, the Lebesgue measurable sets, then the next step is that step 4, the construction is very complicated, that mu star is sigma additive on M. It's not sigma additive on any set, but to restrict a set to this Lebesgue measurable sets, then this becomes sigma additive. So therefore, this becomes Lebesgue measure. This is the Lebesgue measure. So I'm running out of time. So, but let me just, I know it's a little bit complicated to understand for you here, but let me just make a remark for you. So the Lebesgue measurable set are the sets of so you can so Lebesgue measurable set. First of all, I'm now showing you another way to construct a Lebesgue measurable set. First of all, you define what is zero measure set. We actually defined that before. Any of you remember? Yeah, I would use 5 more minutes of your time. Hanwen, do you remember what is a zero measure measure set?
If it's finite countable.
So no, it is, let's say this is E is a set if it can be covered by countable union of intervals where the for any epsilon, okay, for any epsilon greater than 0, we can find ik, those are intervals, so that E is covered by the union of these intervals, and then the sum of the measure of ik, where k from 1 to infinity is less than epsilon. So for example, a point is a zero measure set. Why is that? Because for any epsilon, I can find an interval with length less than epsilon that that cover this point. Any countable set is zero measure. Do you remember how did we prove this? Any countable set is of zero measure. So let's say this set is A1, A2, AN, right? Each of these I would cover for any epsilon, I would cover by, say, this one would be A1 minus, say, A epsilon over 8, and A2, A1 plus epsilon over 8. Then the length of this interval is epsilon 4, and the next one I can cover by even smaller interval. So that is the next one I would have 8, and then the next one I would have this. Now then when I add all this up, epsilon 4, this would be 1 plus 1/2. This would be epsilon 4 times 2 would be epsilon 2/2, which is less than epsilon. So therefore, we prove that any countable set is zero measurable. In particular, the set of all rational number is zero measurable. So that is a good thing. Now, then another way to understand Lebesgue measurable set are sets obtained by countably. So you starting with open sets, countably many open sets, and then you perform countably many, at most countably many set operations like union, intersection, and let me see here. Union, set minus intersections, and then this set, and then this E is, these sets here are what we call is Borel sets or Borel algebra. So this is a Borel set plus Z is any Lebesgue integrable, Lebesgue measurable set is a union of Borel sets. Okay, let me repeat. What is a Borel set? You start with an open set, and you start with a bunch of accountable remaining open set. You just do all sort of set operation. You obtain a set, and this set is a Borel set. So the Borel algebra or the Borel ring is the set of all the family of all sets obtained by countable remaining, at most countable remaining operations from open sets. And this is a zero measure set. So that is how Lebesgue construct the Lebesgue measure on the Euclidean space. Okay, so let me just repeat what I have here. You first define what is the measure of an interval. So in one-dimensional case, it's just for an interval, it's just the length. In two-dimensional case, you have a rectangle, it's just the area of the rectangle. That's easily defined. In higher dimension, it's just a volume. Then you want to generalize. You can generalize this concept of measure to all finite union of intervals. However, this is not good enough because this would not give you a sigma ring, and it would not give you a sigma additive. And this sigma ring and sigma additive is very important, and that comes up later on when we try to find the limit theorems like interchange of limit and integral sign. So then you throw in more things. Then these more things that you throw in are the zero measurable sets, and you generalize your concept of interval to this concept of Borel measurable set. Borel measurable set are those sets that obtained by countable operations from open sets, and that if you restrict your family of sets to Lebesgue measurable sets, which we will use M to denote, then it turns out that the outer measure that you define becomes a measure. So that means that instead of having some additive properties, you have a sigma additive property, and that become a measure space. Once you have a measure space, then next time on Monday, we are going to explain how would you define a Lebesgue integral, and that is what we are going to do next time on Monday. Okay, so go back. My recommendation for you is to go back to trying to read the section 1 to section 4 again by yourself after you kind of getting some idea of what I'm talking about, and we will try to finish the rest of at least the main point of for the rest of the chapter on Monday.
Hello, Professor.
Yes.
Yeah, can I ask something about next semester? Yeah, do we have analysis 3 for our school?
Analysis 3. We do not offer this class for this group. We do not. But let me think about if you want to study this further, then I can do an independent study with you. But talk to me before the beginning of next semester. Then.
Great, thank you, Professor. Yeah.
Yep. Yeah, we do not offer further class of this. Any other questions, Ryan and Paul?
Nope.
No, I'm okay.
Okay, so I will see you guys next time then. All right.
Have a nice day.
Yep, you too.